Good, Good afternoon, everyone. My name is Dongju Lee. I'm a CTO of Lightscale. Today, I'm going to introduce WEMIX Kanvas that we are building to solve the blockchain scalability problem. It is a Rollup-based Ethereum layer 2 platform. So let me start with a short introduction video about WEMIX Kanvas. Okay, these are topics that I prepared for this presentation. At first, I will simply talk about background. Then I will introduce our development strategy, and I will describe protocol details, including decentralization strategy. Finally, I will present current status of WEMIX Kanvas and future roadmap. I believe that a lot of you have thought of blockchain mass adoption. To make more people adopt blockchain, scalability problem should be solved. Ethereum network have reached its throughput limit. It's about just 1 million transactions per day. There have been much efforts to solve this problem, such as sharding, sidechain, plasma, and so on. Some of them can be grouped into layer 2. Layer 2 solves the blockchain dilemma by separating execution from consensus. Layer 2 lowers the fees and higher the throughputs while inheriting security guarantees of Ethereum. Finally, builders can expand their projects into new applications with improved user experience. There are different types of Layer 2 solutions, such as Plasma, State Channel, Validium, Rollups, and so on. We are not going to compromise security and decentralization to get more scalability. Therefore, Rollup is the only practical scalability solution for us. There are two main streams in Rollups, optimistic and GK. Optimistic Rollups are more widely used because they are EVM compatible, but they have the late finality. In opposite, GK Rollups have faster finality, but they are EVM compatible. And this makes it harder for dApp developers to join the ecosystem. To solve this problem, several teams are building GK EVM, but it's not enough because it still takes too much time to generate proofs. According to L2Bit, total values locked in all layer 2s is more than $6 billion. As shown in this figure, TVL of optimistic rollups is about 90% of L2s. Although TVL of GK rollups is increasing, still optimistic rollups dominate the L2 market. From this, it is clear that keeping usability is very important for the success of rollups. These are key features that we defined for our system: security, decentralization, low fee, high throughput, EVM compatibility, fast response, and fast finality. We designed WEMIX Kanvas to include these features. Our philosophy plays an important role of determining many things like development strategy. Before talking about details of WEMIX Kanvas, I'd like to mention our philosophy. The first one is pragmatic. I think it's time to make it clear. So we mainly focus on making something that works properly for the real use cases. Adaptive. There are so many great contributions to the blockchain technology. We adopt them, make it better, and finally share it to the community again. User-friendly. We are always keeping in mind that we have to provide the best user experience. Following the philosophy, we adapt various best practices from existing projects such as Optimism, Arbitrum, Scroll, and so on. Optimism is one of the widely used optimistic rollups. Optimism team have operated Optimism network more than 2 years. Recently, they have been developing Optimism Bedrock. It has inspired our team so much. So we took many things from Optimism Bedrock: modular architecture, rollup and derivation processing, and P2P. These make it possible to bring lower fees, higher throughput, and faster response. Arbitrum's interactive fault proof is very efficient. We adapted it to our ZK fault proof mechanism. Scroll is contributing to the ZK EVM so much. In conjunction with Ethereum Foundation, we basically started with their ZK EVM. Therefore, we will have fast finality in WEMIX Kanvas and EVM equivalence. Based on those foundations, we added our original ideas to make WEMIX Kanvas. At first, we have tried to use GKP to rollups in a way that is practical. So we begin with an optimistic rollup where fault proof is implemented with GK EVM. We call this kind of fault proof as GK fault proof. At this stage, GK proof is only used to resolve dispute challenges because we have not yet optimized GK proof generation sufficiently. After optimizing GK proof generation, we can move to EVM equivalent GK rollups. We designed a smooth transition mechanism from optimistic rollups to GK rollups. Decentralization is one of the important problems we have to address. We have been designing and implementing WEMIX Kanvas where validators and proposals can be easily decentralized. Okay, let's look into more details about WEMIX Kanvas. Network participants, rollup and derivation process, about how WEMIX Kanvas handles deposits, withdrawals, and transactions. There are two things that I'd like to introduce how GK proof is used in WEMIX Kanvas. The one is GK fault proof for optimistic rollup, and the other one is GK proof pipeline for GK rollup. There are three types of participants in the WEMIX Kanvas network: users, proposers, and validators. Users can deposit or withdraw transactions on L2 by sending data to a contract on Ethereum mainnet. Users can submit arbitrary transactions to proposers, just like the layer 1. Proposers accept users' off-chain transactions and observe on-chain transactions. Usually, on-chain transactions are deposit events. Proposers consolidate both kinds of transactions into L2 blocks with a specific ordering. Validators derive L2 chain by reading data in L1 chain. They verify the integrity and also checkpoint. If there is any invalid assertions, validators can also submit dispute challenge on the invalidated assertions. Regarding the network participants, there are some differences between optimism and WEMIX Kanvas. First of all, I changed node names from sequencer to proposer and from verifier to validator. I think this matches well to the participants of layer 1. This makes it more natural to reuse layer 1 components in the similar way. In optimism, sequencers not only submit batches, but also checkpoints. On the other hand, in WEMIX Kanvas, proposers just submit batches, and validators also checkpoints. By changing like this, validators can receive rewards from checkpoint assertions as well as dispute challenges. Consequently, I think this resolves verifier's dilemma. Let's see how L2 blocks are loaded up to L1 by a proposer. L2 blocks are built with L2 transactions from mempool. L2 blocks have reference to the L1 block so that deposit transactions in the L1 blocks will be properly included in the L2 blocks later. As shown in this figure, L1 deposits are stored in the first L2 block just after the L1 block. L2 blocks are more frequently created than L1. For now, L2 blocks are created at every 2 seconds. So several L2 blocks are encoded and compressed into a channel. Then the L2 channel is split into channel frames so that each frame can be stored in a single L1 transaction. A validator can read channel frames from L1 blocks as well as deposit events. Then the validator can reconstruct a channel from these data. And finally, L2 blocks can be built from the channel and deposit events read from L1. These processes are managed by multiple components. Just like the L1, the execution engine manages mempool, builds L2 blocks, manages states, and serves RPC requests from the user. The Rollup node requests to build a block to the execution engine with proper payloads. The batcher manages channels and channel frames and submits channel frames to L1 network. The Rollup node in validator reads frames from L1 blocks and derives L2 blocks. The Rollup node uses engine APIs to build the L2 blocks. There are some complicated issues that we have to consider when we implement Rollup and derivation processes, but I skip them in this presentation. Okay, let's see how WEMIX Kanvas handles deposits and L2 transactions with these components. At first, users submit deposit transactions to layer 1. Then the Rollup node watches deposit events and creates payload attributes with the deposit transactions. The Rollup node calls on engine API so that the execution engine creates a block with the payload. Users submit L2 transactions to the execution engine. Then the submitted transactions are included in blocks when the Rollup node calls engine APIs. The batcher gets the latest block cache from the Rollup node and then reads the block body from the execution engine. Then the batcher submits the blocks to the batch inbox in L1. The Rollup node in a validator gets blocks from batch inbox and transforms them into L2 block inputs. Then the Rollup node requests to create blocks with the payload to the execution engine. The validator components get the latest checkpoint output from the Rollup node. The validator component submits the output to L2 output Oracle contract at every 1800 blocks. With 2 seconds block time, it is 1 hour. Output root is generated with the version type and payload. Same version number means that the structure of a payload is the same. In the current version, payloads are made with state root, withdrawal storage root, and latest block cache. Output root will be used for confirming withdrawal from L2 to L1. For a user to withdraw his assets from L2 to L1, he has to submit a withdrawal initiating transaction to L2 contract first. Then a proposer node posts batches with withdrawal transaction data to batch inbox. A validator gets the blocks and also an output that contains withdrawal commitment. The user needs to wait until the block is finalized. After block is finalized, then the user can request to finalize the withdrawal to the bridge contract. Bridge contract verifies the transaction with the output route by checking if the withdrawal storage route contains the withdrawal data. If the transaction data is verified, the user finally gets his asset. This figure shows the overall architecture of WEMIX Kanvas without dispute challenge. Currently, we are using modified Go Ethereum as the execution engine. Therefore, built-in peer-to-peer network and transaction pool is used to propagate transactions. The same network is used to propagate submitted blocks and support snapsync. Ethereum creates blocks at every 12 seconds, but Kanvas creates at every 2 seconds. Therefore, there may be unsubmitted blocks in the property yet. Those unsubmitted blocks are called as unsafe blocks. They are propagated through another peer-to-peer network of Rollup nodes. Using those two peer-to-peer networks, execution engine can respond to user requests with low latency at every node. Until now, validators only act as an asserter. Now let's see how validators act as a challenger. Let's assume there is a faulty output that is provided by another validator, that is an asserter. At first, the Rollup node of this challenger gets block data and transforms the data into L2 block payloads. The Rollup node calls an engine API with the payloads. Then execution engine builds block. This validator component reads an output from the L2 output oracle and also reads the corresponding local output from the execution engine. Then compares them. If the assertion output is different from the local output, the validator submits dispute challenge. To resolve the challenge, the validator first needs to find where the difference starts from at a single block level. After finding the block, the validator component requests to generate a GK proof to the GK prover. The GK prover gets execution trace for the block from the execution engine and generates a GK proof. The validator component submits the proof to the L1 contract. Then the GK verifier contract verifies the proof. If the proof is verified, the challenger wins and gets the rewards. If the proof cannot be verified, the challenger loses and his staked assets will be transferred to the asserter. Let's see more details about these two parts. When identifying a faulty output, we begin with the two checkpoint outputs. The first checkpoint output should be the same to the challenger's local output. Between those 1800 blocks, there must be an initial block where the challenger's output and the asserter's output are different. The challengers get to know the initial block position by interacting with the asserter, who submitted the faulty checkpoint output. At first, the challenger submits 46 output loops that evenly distributed between these blocks. Then the asserter compares these outputs to his local outputs and finds the first different output. Then the asserter submits all the outputs between those blocks. Again, the challenger compares those outputs to his local outputs and finds the oldest different block. Then the challenger generates a proof that shows his output is valid and submits the proof to the Colosseum contract finally. This figure shows the state transitions in the Colosseum contract. The challenger starts a challenge by staking his asset in a checkpoint. Right after staking his asset, the challenger submits output segments and an asserter should respond to within a time limit. In most states, there are some time limits so that the challenge processes ends within the reasonable time. In the previous example, the faulty The faulty block was found with just 2 interactions, but there may be more interactions with different segmentation schemes. Interactions must be an even number so that a challenger can start the interaction and submit the proof after the assault turn. We tested several segmentation schemes. Among them, this 5, 9, 8, 9 segmentation scheme consumed the least gas. We inherit GK EVM of EVM Foundation and Scroll. To reduce the probing time, we use a GK try instead of a Merkle Patricia try. We use Poseidon hash instead of Kekak, and GK try to compute the path to account or storage slot. We added additional specs for layer 2, such as L2 deposits and load-up gas fee processing. This shows the circuit structure. There is a super circuit that embeds many circuits designed for the specific purposes. With these public inputs and this private input, we can obtain a block proof. Circuits are not fully implemented yet, but I hope it will be finished soon. Yeah, this is the previous architecture without challenging. Now we have the full architecture. Those are additional components to use zero-knowledge proof in optimistic load-ups and GK load-ups. WEMIX Kanvas have GK-friendly data structure and hashing schemes from the initial stage. Therefore, even though we start from the optimistic load-up, we can move to GK load-up without heavy migration process. At the GK load-up, validators act as provers. They also take point outputs with a GK proof. Okay, let's see proving pipeline. Once a block is created, a prover will generate a proof for the block. While blocks are created at every 2 seconds, generating a proof usually takes much more time. So multiple provers need to generate proofs in parallel at the same time. In this figure, except the first proof, others include previous proof in their proofs. Then the checkpoint can be verified using only one proof. Created proofs will be propagated among provers through the peer-to-peer networks of Rollup nodes. If we submit the checkpoint with a large interval, large public input should be addressed to verify the proof. If we submit the checkpoint with a small interval, the cost to submit checkpoints will get higher. Therefore, when we move to GK rollups, we need to determine the proper checkpoint interval considering these trade-offs. If we reduce the probing time sufficiently, we can move to GK rollup. There must be a coordinator for the transition. In this figure from the block BI plus K, a checkpoint output is verified with a proof. After the challenge period, the network can be considered as a GK rollup without any further changes. There must be more issues that we have to address. This is the basic idea how we can transit from the optimistic rollup to the GK rollup. There are 2 types of decentralization in WEMIX Kanvas: validator decentralization and proposer decentralization. At the first phase, we are focusing on validator decentralization. I mentioned before, validators can get rewards by asserting checkpoint as well as challenging invalid checkpoints. This will motivate node operators to join WEMIX Kanvas as validators. We are finding proper parameters for the stakes and rewards for now. We are going to use trusted execution environment when we adopt proposer builder separation. I think this is simple, but can support strong censorship resistance and blocks MEV abusing. Currently, we are researching in conjunction with external research teams for this issue. I hope we will have practical implementation for this in the near future. There are many challenges that we have to address. The first one is GKP optimization, which is what we are focusing the most at this moment. We are using Poseidon and GK-Try. These make execution engine work slowly. So optimizing execution engine is another important issue we have to solve. We need to modify our components according to the proto-denk sharding. And I already mentioned the PBS just before. We will support account abstraction in WEMIX Kanvas as soon as possible. This is our roadmap. We have finished the POC, and now we are preparing to open our public testnet within a month. At this time, there will be a single proposer and multiple validators operated by private members. GK-EVM will work, but not cover all the specs yet. We will support full peer-to-peer propagation, which means you can have fast response time at every node. I hope that we have an EVM equivalent GK rollup in the next year. Yeah, you can visit this site to see our teaser, and you can check our source codes in this GitHub soon. And we are going to provide full resources when we open our first testnet. Thank you for your attention. Do you have any questions? Yes? I'm sorry? You mean the testnet timeline? Mainnet. Yeah, we are planning the third quarter of this year, but it starts as an optimistic rollup.
You want to see the video again? In full screen or in this screen?
I'm sorry? Actually, we are not have any plan to issue tokens for this layer 2. So, thank you. Have any question?